Alright guys, this is just going to be a little quick intro into the nuclear chemistry. We're really not going to get that far into it. This might be as far as we get. But we're just going to quickly recap maybe I should fully spell that, the four fundamental forces, or as I like to call, the four fundamental forces. See what I did there? So, these four forces essentially account for everything that happens in the universe, or at least how matter interacts with each other, and what we can detect. There might be more, or there might be some hints that there's more, but for now, this is all we need to focus on. So for the final, all you need to know what to do is to draw them or to identify them on an atom and what they do in relation to the stability of an atom and things like that. So first one we're going to start out with is probably going to be the one you are most familiar with, and that is the electromagnetic force. Okay, that is the force of positive charges and negative charges, right, attracting. So there's going to be a pull. So think about it. Why does that occur? Well, that is the result of these positive and negative charges within atoms. And if we have a positive charge and a positive charge, they're going to repel, right? Same thing with a negative charge and a negative charge. So like charges repel, positive charges attract. That repel. Right? That is one of the four fundamental forces. This is the, I could say, the second strongest. Okay, where does it take place? Well, we have our nucleus here. Nucleus is going to be positively charged. And we got our atoms zipping around all over the place. And there's our Jimmy Neutron model, aka the Rutherford. Those electrons are negatively charged, right? So that's why there is an attraction between them. There is a pull from the proton to the electron, and that is the electromagnetic force. This accounts for basically all of chemistry, or at least how electrons interact with matter, right? So pretty important for us. But well, and they don't crash into each other, right? Because they only exist in certain orbits, and for the most part, if it's a non-radioactive atom, it is fully stable. So this is just going to zip around forever and ever until something happens, and it doesn't. But this is a stable system, I guess you can say, right? They pull on each other, and that's why we have these zipping around and everything like that. Next one is going to be the strong force. Okay, that is going to be the force that binds nucleuses together, so nuclei together, so subatomic particles, right? So we just talked about the electromagnetic force, how same charges repel. Well, think about it. Our nucleus of an atom, if we were to zoom in, we got a proton here, which is positively charged, but in a nucleus, it's going to be very close to another proton. Sorry, if I said it, that's a neutron. We have a proton here, proton here. It's going to be close to another. Of course, we also have neutrons, which lack a charge, zero charge. But think about it. How do we have a nucleus with these positive charges, and they don't break apart and repel each other? Well, that is the result of the strong force, I guess you could say. So we'll have, all right, here there is a very, very strong force keeping protons together there. Otherwise, why doesn't a nucleus just break apart? Well, the strong force. So when protons, neutrons touch each other, the strong force takes over and does not let them push each other apart. So extremely strong binding power. So this is by far easily the, well, I was going to put number one strongest of the four forces, strongest force. Okay, so that is inside of the nucleus, why it doesn't pull itself apart. Okay. Next one, we're going to talk about the weak force. So the weak force. Okay, so the weak force, we'll say, changes the contents, we'll say, changes the contents of nuclei or nucleuses or subatomic particles or subatomic particles. So we know, or you should know, that there's something called radiation, right? So atoms, even though they're very stable, they're not, well, some are permanently stable, but not all of them are very stable. So some atoms, let's say, there's your nucleus, got your electrons zooming around. All right, some atoms emit particles, so radiation from them. How does that happen? What is occurring that is allowing particles inside of a nucleus to be flung out and also to change the nucleus? So how is the electromagnetic force and strong force overcome? Well, that is with the weak force. So if we were to zoom in inside of an atom, this is supposed to be a proton, right? Protons and neutrons are made up of quarks and other subatomic particles. So the weak force takes place, occurs, we'll say, over extremely short distances. So even though we have the strong force, which is very, very strong, holding the atom together, the weak force can, if some of these get close enough, or not close enough, but under certain circumstances, they can be ejected, right? So sometimes, where I'll draw, we'll say this is a proton, we'll say this is a neutron. Sometimes a proton can turn into a neutron, right? Or at least it can, some of its constituent particles can change, and then when that happens, you might get a piece of radiation flinging out. For now, all we need to know is that it would be an electron. Okay, so the weak force is going to be the third strongest. It really accounts for radiation and things like that. So this takes place even further inside of the nucleus of an atom. And then lastly, we have the gravitational force. Okay, this is actually the weakest. Gravity's weak, so weakest of the four forces. You guys see that? Oh, gravity is actually the weakest of the four forces. Okay, and the electromagnetic force also occurs over unlimited range. Same thing with gravity. Gravity actually is stronger over a larger range. So unlimited range. So even though there's pieces of matter that are on the other side of the universe, they do exert a gravitational pull on you. A charged particle might also exert a force on you, but it's not as strong as a gravitational force if it was on the other side of the universe. It's an extremely small force, but it would still do it. It has an unlimited range. However, within an atom, so within the nucleus of an atom, all right, you got everything zooming around. If you were to zoom in, right, on, let's say these are protons. So there is actually like almost zero, let's say. There is close to zero, and literally zero, not like, oh, you're talking about a really small number? Yeah, but there's much stronger electromagnetic force between a proton, between two protons, so two repulsive, right, up two positive charges. There's much more of a repulsive force from the electromagnetic force than there is a gravitational force. There's something, it's a ridiculous number, something like 7 quintillion times. So the electromagnetic force between two protons is like 10 trillion times stronger than the gravitational force between two protons. So it's close to zero on the atomic level, but in the macro level, so the level that we experience, right? You experience this every day. There's gravitational force between atoms, right? So in the large scale, gravity does a lot. In the small scale, gravity does not really mean much for us, okay? This is just a really quick recap. We're going to talk about this in a little bit more depth. Probably won't go into a lot how it's going to relate to radiation today. All right.